MP3 is one of those constants in life which we just accept as being there. The way you make them, though, is actually more interesting than you'd think, and much weirder. So let's dive into one of the weirdest technology of the late 80s and early 90s. If your eyes are glazing over at the sight of this amazing flowchart, don't worry, it's not that awful. It gets easier if we look at the blocks one by one. So, starting with some completely ordinary audio data, let's begin with the FFT. The fast Fourier transformation, or FFT for short, is probably one of the most important algorithms humanity has come up with. They can convert between a waveform, a time series of a signal usually representing loudness or sound pressure, to a frequency spectrum. Which frequencies of the sound we were just listening to are the loudest? Knowing what frequencies are the loudest is incredibly helpful for a later step to do its magic. I won't go into depth on exactly how FFTs work. That would be an hour-long computer science lecture all on its own. The important thing for us to know is that it converts between the time domain and the frequency domain. It does, however, come with a quirk we need to be aware of: the uncertainty principle. Let's compare a single sample of audio to an entire concert. For the single sample, the FFT could very easily determine when that sample occurred, but we wouldn't know the overall shape of the sound. For the recording of a concert, the FFT would be able to expertly map out all of the frequencies, but we no longer would be able to pinpoint at what time in the concert things happened. This is the basis behind the uncertainty principle. And yes, this uncertainty principle is the very same one that Heisenberg is famous for. At the end of the day, both quantum physics and audio physics just involve waves. For this reason, there are actually two FFTs being produced. One FFT which entires the entire chunk of audio to get all the frequencies, and another one which has a much shorter window and is used to find out where the transients are. Transients being drum hits, claps, and other very short events. The uncertainty principle applies to pretty much anything in audio processing, not just FFTs. For example, you cannot have a filter or an EQ where the audio immediately turns louder once it hits a certain frequency. The best you can do is something that gradually ramps up until it hits a frequency and then ramps down once the sound goes higher. I'm telling you all of this because it's relevant for our next point in the journey as well: the Filterbank. While the FFT is doing its thing, the audio is also sent through the analysis Polyphase Filterbank, which incidentally is also what I'm calling my upcoming proc band. The Filterbank is used to split up the audio into 32 subbands containing a much narrower range of frequencies. Here is what this would sound like if we just used 3. Lowest subband, middle subband, highest subband. This Filterbank is quite unfortunate for MP3 for 2 reasons. This is, for one, because the filters leak a bit into each other due to the uncertainty principle, causing some distortion. In fact, about 20% of the distortion that happens during MP3 encoding is just due to this Filterbank. And the second reason, the Filterbank is entirely unneeded for MP3. Instead, it's the technology used by the simpler MP2, which skips a bunch of the upcoming steps and is entirely pointless for MP3. But because MP3 is meant to be a computational layer on top of MP2, hence the name MPEG Audio Layer 3, it has to put up with this substandard arrangement. But anyway, once the audio is passed through the Filterbank, the problems aren't actually over. Because the Filterbank doesn't convert to the frequency domain like an FFT would, we still have regular audio files at our hand, but now 32 of the things. That's a lot of data. So to combat this, the Filterbank now just destroys 31 out of 32 samples in each subband. The remaining 3% of the data is sent to the next step, the MDCT. MDCT stands for Modified Discrete Cosine Transformations. To get any clue on what that could be, let's look at regular discrete cosine transformations first. And surprise! It's FFTs again! Sort of, anyway. See, I lied a bit earlier. FFTs don't just convert audio between regular waveforms and frequency spectrums, they actually work on a complex plane, i.e. the thing where imaginary numbers occur. The data in this extra dimension is used to encode the phase of waves, where phase means whether a wave starts at the top, the middle, or the bottom. To simplify our lives, the DCT simply gets rid of this phase data. I already can hear you think, but why? Why go through the trouble of having an FFT earlier, only to now put out a slightly different version of it? The answer is quite simple: because it compresses better. Here's an example of some JPEGs which have been encoded with DCTs and FFTs respectively. You can see that the FFT preserves a lot more fine detail, which means that instead of getting blobby at high compression rates, it instead becomes noisy. DCTs don't do that, because the data already has been simplified, and so the end result is much more recognizable for our monkey brains. However, the FFT is still superior for analysis, which is why the psychoacoustic model uses that thing instead. Alright, with me still? Now it's time to talk about the modified DCT. In JPEGs, which are just using the regular DCT, a common issue at higher compression rates is a certain blockiness. This is because JPEGs are divided into blocks and adjacent blocks are encoded separately. For JPEG this is sort of fine, but for sound, choppy audio would be unbearable. So the smart minds have extended the DCT algorithm to also look a little bit of the previous analysis frame and a little bit of the next one. This allows them to effectively blur the blocks, which sounds a lot more natural. In the big picture then, the MDCT is used to divide the subbands that came out of the Filterbank into 18 so-called spectral lines. How each subband is split up depends on what the psychoacoustic model believes to be better. When trying to preserve transients, 3 short windows with 6 spectral lines are used. When trying to preserve frequencies, just 1 long window at 18 lines is used, which may or may not look at the previous and next window as well. Both options introduce a little bit of time smearing, but for the long window it's a lot worse than for the short ones. As this processing is being done on each of the 32 subbands, we end up with 576 spectral lines. We so far have neglected to talk about the psychoacoustic model. The Psycho has been orchestrating the MDCT and will orchestrate the scaler in a second. So what does it actually do? In short, the Psycho is an expert in manipulating us with illusions. Just like optical illusions trick the brain into misinterpreting what our eyes see, auditory illusions trick the brain into misinterpreting what our ears hear. Of particular usefulness for MP3 encoding is sound masking. Sound masking is when a tone is there, but we cannot hear it. This happens in various ways. For example, when a tone plays at the same time as a much louder tone of a similar pitch, we can't hear the quieter one. If a quiet sound is played just before our loud sound, we can't hear the quiet sound either. And if a sound is buried underneath white noise, well, have a guess. And what we can't hear, MP3 doesn't need to store. The way the psychoacoustic model works internally is complicated, and in fact there's a bunch of different models out there. But in very brief, a core concept is figuring out the just noticeable distortion, so it knows how far to push the envelope. It then undoes all of the things the Filterbank did, as the subbands that came out of it are completely useless, figures out what can be masked, and ultimately produces a signal-to-mask ratio for every spectral line. This ratio is basically the importance for each frequency. A high signal-to-mask ratio means that we can definitely hear that frequency, and it should only get removed as a last resort, whereas a low ratio would be a good candidate to throw out early to save some bitrate. All of this then goes into the scaler and quantizer. This is definitely the step which is the most complicated. We have our inputs from the 576 spectral lines, and info on what we need to worry about from the psychoacoustic model. These lines now need to get quantized. Quantization here means that the values in these lines, which at the moment are a bunch of decimal values, need to get reduced in precision by rounding them to something simpler. This is what drives the core compression performance of MP3 and is the main source of lossiness. However, we can do something to help them out. See all of these numbers down there, very close to 0? If you quantize them as is, they would end up all being rounded down to 0, which would be noticeable. However, if we scale them up first by multiplying them by 1000, for example, now these numbers retain a lot more information than they did before. This is what the scaler does. However, we also need to store the scale factor, so there are some additional bits we need to allocate to make this work. MP3 encoders then dance around a lot to figure out where bits are used best. Do we keep more precision in the original numbers, or is it more efficient to use a scale factor here, and if so, which one? Individual spectral lines aren't given their own scale factor, but instead are grouped into so-called scale factor bands, where each band closely resembles what our ears and brains would be doing, with a concept called critical bands. Again, the subbands we got out of the Filterbank at the beginning are completely the wrong shape to work here. The scale factor bands then get their scale factor compared between the channels too. Wouldn't it be nice if you could just reuse the factor from the first channel on the second one as well? Also, imagine we could get all the values to be the same. If we could use Huffman coding to add another layer of lossless compression at the end of our compression chain. Huffman coding works like a zip file. In fact, it's the exact algorithm used in zip files, together with LZ77. The exact way it works could fill yet another computer science lecture, but in essence, it figures out what numbers or letters come up with the most frequency, and gives those the shortest code. This can reduce the representation of a 32-bit integer to as little as 2 bits in the best case, provided we keep a table around on how to decode this. Now, we are almost done. We have already stored the data we wanted, but how does the decoder know how to interpret the data? That's what the side info is for. It includes data offset, scale factors, Huffman tables, window length, what sort of stereo mode we've been using, and so on. All the stuff that's needed to reconstruct normal audio files afterwards. This data is then assembled into the bitstream, which are MPEG frames. Each frame contains a header, a CRC, which is a checksum in case the MP3 frame breaks during a transfer, the site info, and the main data, and if you want some ancillary data, which can be anything you'd like and probably isn't needed for decoding. All of these frames are then put back to back to back and assembled into a file, and voila, you have an MP3 file. But let's take a quick look at the header again. We start out with a sync word, which is 12 bits of ones. This is basically a digital shout saying, hey, new frame starts now, pay attention. Following this is the MPEG version and layer. This determines what bit rates and sample rates are available, and a bit telling us whether a checksum has been used. Following that comes bit rates and sample rates, and then padding info. Why padding? Because audio people insist that 44.1 kHz is a good sample rate, but that's not a nice power of 2, so sometimes encoding doesn't work out as nicely as the computer people would like it to. In that case, padding is needed. Following that is a private bit, which just means, hey, I've done something non-standard, only I know about. Followed by mode and mode extension, which tells us whether or not we are in mono, stereo, or what sort of stereo. There are actually different versions of stereo, but that's a video for another time. And finally, last and definitely least, are the political bits. The first one is a "is this file copyrighted" bit. Just that. It doesn't know who the author is, when the song was made, so it's completely useless in a legal sense. But some copyright maximalist wanted it there, so now it is there. The next bit says, is this the original encoding? Which, given that we just started with a pre-existing audio file before going onto this entire endeavor, is a bit daft as well. And finally, emphasis. In the 80s and 90s, Dolby had the idea of doing noise reduction by applying an EQ on some audio, compressing it, uncompressing it, and then applying the EQ backwards again. I have no idea how this would work theoretically, but I do know that practically nobody ever does this. So here we are, a standard 32 bits in the header, with the last 4 bits are pointless, so hey, good enough. Except, said Fraunhofer, the creators of MP3, what if it wasn't? So they went ahead and worked on a third version of MPEG, using even shitter bitrates, even shitter sample rates, and introduced it as MPEG 2.5. And because Fraunhofer is special, they didn't use the private bit for this non-standard operation, but instead they ate into the sync word, which now means we have only 11 bits of ones in the header doing the syncing, which is unheard of anywhere else in computing. Good job, guys, really saved the day here. And just like that, you have learned how MP3s are encoded. Probably, anyway. You see, the final curveball that MPEG throws at us is that they actually never specified any of this. All they specified is the decoding process. So every encoder has some wiggle room in how things are done, diverging somewhat from this procedure. But probably not too much, because again, the decoding steps are fixed, so you need to figure out how to match those properly. Thank you very much for watching. My name is Leo Wattenberg. If you liked the video, give it a like, and I hope to see you next time.